Good morning, everybody. Uh, Thank you for coming to this presentation of about smart modeling for water quality prediction for resource management system. This presentation will be made by Marwah Helaly, that is an assistant professor at the Department of Computer Science and Ain Shams University in El Cairo, Egypt, and she is a professor in that university, and now is developing his PhD. He will introduce us in some deep learning techniques and methods in order to predict the quality of waters in areas that she detects that is a heavy problem or a big problem in mainly in the city. Without no more presentation, thank you for coming. We are proud you are here visiting us this week, and it's your time. Thank you.
Thank you. Thank you. Hi, hola. How are you doing? Everyone okay? Okay, so I'm Marwah Ahmad Helaly. I am, yes, an assistant lecturer at Ain Shams University in Egypt, and I work in several positions in my university, and I also work as a data analyst. So I took my master's degree in DNA sequence classification using deep learning methods. And I'm just starting out in my PhD study, and my topic is smart modeling for water quality prediction and resource management systems. So today we're going to review the motivation behind why this is needed, especially in Egypt, because I intend on applying it on Egyptian water. So why it is needed, and what are the recent researches that have been done in many countries around the world for this purpose. Um, So, as an introduction, we all know that water is an essential need for all living beings on Earth. Water isn't used in one way; it's used in many ways. So it can be used by normal people for domestic use. It can be used for industrial purposes, recreational purposes, or agriculture. So it's used in many ways, and the water quality differs according to where I'm going to use it or how I'm going to use it. Um, Unfortunately, much of Earth's resources are heavily polluted. It differs from country to country, but in general, it's a known problem around the world that our water is unfortunately polluted. So in 2015, the United Nations released the 2030 Agenda for Sustainable Development, where they listed 17 SDGs. So, water quality and resource management can or targets a specific goal of them. So, it targets specifically goal number 6, which aims for clean water and sanitation. And when we achieve clean water and sanitation, we consequently will be able to provide good health and well-being to all living creatures on Earth, and we'll be able to benefit the industry and innovation and infrastructure of the country. Um, Given all of these SDGs, the United Nations has still put water quality has made water quality one of the essential priorities. So we have like a metric called the Water Quality Index, so WQI. The Water Quality Index is a very popular measurement in water quality in general. It's generally a single number, but that single number it combines multiple water quality parameters together. This provides merging all the parameters into one number provides several advantages. Number one is that it standardizes values. It also simplifies the entire operation in visualizing the data, and it decreases the volume of the data that we need to store. So we don't need to store like huge vectors and many samples for each. So it just decreases the volume of the data that we need to store. So the water quality index, as we said, it's a parameter, or it's a measurement that is calculated from many different parameters. These different parameters could be physical, biological, and chemical, and it can include time series information as well. We'll have a look at the different types of parameters that can be included in the WQI models. So the main research problem is that the WQI measurement or model is used um, everywhere around the world, specifically in these places that are colored, but unfortunately, it's not used in Egypt at all. And Egypt's water is unfortunately it's heavily polluted by many different things. So especially the Nile, it's polluted by domestic waste and industrial waste. So it really is heavily polluted. So the different water quality indicators, when we have a certain water resource, the different indicators that we can like retrieve from the water is biological indicators. So these possibly physical indicators like water temperature, total suspended solids, and etc. Chemical indicators, where the most common two chemical indicators are the biochemical or the biological oxygen demand of the water and the chemical oxygen demand, and commonly time indicators. So as we'll see together, water problems are usually a time series problems. So usually time is one of the indicators with us. Uh, as we said, Egypt's water is heavily polluted, and the conservation and the cleansing of Egypt's water is one of the country's top priorities. There's something called surface water, the water above, and then there's something called the groundwater. So the surface water, unfortunately, this is the water that is like it's more used by the public, by all the people. So this is the layer, the type of water that is usually heavily polluted. But unfortunately, that water seeps into the groundwater, so it pollutes the groundwater as well. So we have like two issues here. We have the surface water pollution and the groundwater pollution. So many people or many researchers from many countries around the world have attempted to predict water quality for their different water resources by different ways over the last few years. So some people have tried traditional statistical methods, and these are usually like a long time ago, such as Markov models, but these are generally too simple and too shallow to be able to efficiently deal with the complexity of water data. Then there's traditional machine learning methods like support vector machines and standard artificial intelligence networks, artificial neural networks, sorry. And they work to an extent, but unfortunately, again, since the water data is very complex, they are not able to efficiently generalize over that water, and they tend to overfit over the data. So the current path or the current way of research these days is deep learning, and specifically hybrid deep learning, where we try to use different types of deep learning methods to target different issues in water data. So for example, as we will see together, some people use like a CNN, a convolutional neural network, and an LSTM, a long short-term network, together to be able to target or solve specific water data problems. So once we predict water quality, or in general, what do we do with it? Does it like give us a number and then we just like take the number and go home, or what do we do with it? It's used for, or it's needed critically for water resource management systems. So water quality information in general is used for is used by domain experts. Given the water quality information that they will get, it's used by them to be able to make efficient decisions when there is some type of hazard or some type of catastrophe, like a chemical leak into the water. So the water quality index or water quality prediction is needed for water resource management systems. Oh, any questions until now, or do we keep the questions at the end? Yes, of course. Yeah. Um, Yes, exactly. For prediction, classification, or prediction. And there are several ways that we try to predict water quality, as we'll see, different researchers try different methods. So some of them predict individual parameters like the biological oxygen demand. Some of them try to classify the water given these input parameters. Some of them try to classify the water into classes. So this water can be used for like areas with sensitive fish, and this water can be used for areas with more stronger fish, and this water needs treatment. So there are many ways that people classify the water. But yes, it is used for future prediction. For the data set information? Yeah. Um, I'm not really sure. I haven't really researched into that yet, so I'm not really sure how long into the future and how we like give it the uh how we set the period. So to say like I want to predict 1 year into the future or 2 year into the future, I haven't really looked into that yet, but it's one of the points. Yes, yes, most probably yes. Yeah. It's the time that this water sample was taken. So as we'll see in some works coming, the samples are retrieved from the water resources, possibly like every hour. So the difference in like I have a single point of a water source right now. This water source, every hour for the last 3 years, I have its data set. So I need to learn how the water changes, how did the quality change when XYZ happened. So yeah, we'll see. We'll see in a little bit. Yeah. Mm, yeah. Yes, that's true. Yeah. Mhm. A spatial prediction. Yes. Yes. Mm, yes. Yes. Mm,
That has in the past influenced some other variables like
yes.
health.
Yes.
So I have to make a study about health,
Mm-mm.
then I have data of the past of what has been the main illness in some areas,
Yes.
but
Yes.
I don't have water quality data of the past
Mm,
because I have not measured.
yes,
So
that's an issue. Yes. Mm,
generate water quality data of the past that I don't have. So for this is also a kind of prediction. So
yes.
many times we think always of predicting the future,
Mm.
but we don't know the past.
An interesting point. Yes. Yes, that's an interesting point. Yes. I should look into that. I could, or I would like comment, a small comment. In different locations, people when they usually research, they take like if I have a big water body, they take different locations, data from different locations in that water body. So sometimes, yes, truly, not every location has the exact same data. They don't have all the same sensors, so there's some missing data and here and there. So some researchers have tried to be able to train a network and give it some specific information and try to let it predict the other parameters that I don't have. So they've been trying to find the relations between these different parameters. I think one of the works here did that. Yes, but this is a very important point that I need to write down. Okay. Okay. Any more questions? Thank you. Uh, okay, so now we're going to move on to see what the other researchers have done in the previous years. So we're going to review 8 different works. Um, They're like ordered from the newest to the older ones. And I concentrated on in the new years and the recent years on Egypt because I want the water research to be done on Egypt. But we have China, other research that has been done on China and Greece and Malaysia, India, China, and Norway. So now we'll look into what they did, the sizes of their data set, what methods they used, and the performance that they got. So the first paper was in 2022. It was on a water body in Egypt called Bahr al-Baqar. And this specific water is used for irrigation. The researchers used a dataset size of 105 samples, which is not big at all. Every sample from these 105 samples had 6 parameters. So the Kelly ratio, the SSP, the PS, the PI, and etc. And I would like to note something small, that these are not the normal parameters that we saw before. So if we went back here, these are not these normal parameters. So they took these measurements from the water and they put them into equations to calculate other things like the Kelly ratio and use those as their parameters. And their target was to use, they tried different machine learning and regression models to be able to predict the water quality index. So they tried support vector machines, extreme gradient boosting, random forest, stepwise regression, principal components, partial least squares, and ordinary least squares. The best performance for them was the stepwise regression model, but we need to like go again and renote that their data set size is really small. Like 105 samples is not big at all. So that's the first paper. The second paper was on a different water resource called Wadi Rayyan in Egypt. They had a larger data set size, so more than 1,000 samples from 7 different locations in the lake. So every sample had exactly these 4 parameters, and they used this data set. They used it on 3 different neurofuzzy inference models. So a neurofuzzy inference model is like a fuzzy model and an artificial neural network together, like this. So they used 3 different models where these 3 different models differ in the number of nodes that they had. And they tried to predict individual water quality parameter indicators. So for example, they would use all of these as input and try to predict the BOD or try to predict the NH4, for example. The best model out of the 3 models that they tried was the model, the second model, which had the largest number of nodes. So we could take this piece of information and deduce from it that when the dataset size got a little bit bigger, the network that had a larger number of nodes performed better. So consequently, we could assume that when we have an even larger dataset size, the deeper networks would probably perform better. Then we have a paper on the Yellow River in China. This is an hourly time series data from January 2018 to December 2020 from 4 different locations in the Yellow River. Every sample, they didn't really mention the total dataset size at the end, but every sample, it's a big dataset size since it's an hourly time series. But this dataset, every sample had exactly these 6 parameters, and they used a hybrid convolutional neural network and a long short-term memory together to be able to predict only the cod of the river. This hybrid deep learning network for them, it decreased the mean square error and root mean square error in comparison to other related works or other methods. It decreased the errors by these percentages. So the hybrid deep learning methods, we deduced that they were quite effective on the larger data sets. Then we have another paper on Kastoria Lake in Greece. This is also an hourly time series from November 2015 to March 2018, approximately 3 years, from 4 different stations. And every sample had these 7 water quality parameters. And they used 4 feed-forward deep neural networks to predict the dissolved oxygen in the water. But this paper, it faced one of the issues that you had kindly mentioned, that they took the water, the data set from 4 different stations, but not all the stations had the same sensors. So like if you look here, you can find here all the parameters, but here only 4 parameters. So and above 4 different parameters. No, they're the same parameters. Sorry. Different networks worked better for different locations because not all the data was there in all 4 locations. So yeah, there wasn't a specific here in this work. There wasn't a specific model that provided the best performance for all the water, and it just differed according to every location. Then we have the Klang River Basin in Malaysia. They had 2 different experiments. They had a small experiment that took data from 5 different stations, and then a larger experiment that took data from 19 different stations, where these were the water quality parameters, or the parameters for every single data sample. And they used they compared 3 different machine learning methods. So they tried a deep network layer with only 3 hidden layers, a random forest, and a decision tree to predict the WQI. So this work actually tried to classify every water resource into the type of usage it can be used in. So class 1 is this is clean water, doesn't need treatment, and it can be best used for the rare fish, the sensitive fish. And this needs like a little bit of treatment. This is for recreational use. This needs extensive treatment. And this last class means that this water can only be used for irrigation, for agriculture, or very strong fish, not sensitive fish. So given that they did 2 different experiments, a small experiment and a big experiment, the small experiment, the best machine learning model that they got was the random forest with 89% accuracy. But that's on the small experiment. On the larger experiment from the 19 stations, the better model was the deep learning model. It gave us the highest accuracy of 87.8 accuracy. We have then the Yamuna River in India. This was also a time series data from 6 years from 5 different locations in the river. These were their parameters, and they tried a lot of different models. So they tried a support vector machine, random forest, linear regression, a standard artificial neural network, a standard LSTM, then a CNN and LSTM together, then a CNN by LSTM. So they compared all of these together to be able to predict individual water quality parameters. So we have these 9 parameters as input, and they would try to predict the dissolved oxygen, for example, or try to predict the pH level. So the best performance for them was the CNN by LSTM, where when they tried it on the COD measurement or the COD prediction, it provided the smallest error of 0.015, and similarly on the BOD prediction. So out of all of these, when we try to predict these 2 parameters, the CNN by LSTM performed the best. Then we have this in China. I don't know how to pronounce it, but Gubiku in China. This was also a time series problem. They collected data every 4 hours. So they had almost more than 10,000 pieces of data. And these were their water parameters, only these 2. And also they tried to predict, their goal was to predict these individual parameters. So given these as input, I'm going to try to predict the dissolved oxygen, or I'm going to try to predict the chemical oxygen demand. They tried 11 different models and compared them together, including the standard LSTM, standard artificial neural network, and a standard LSTM, and then an LSTM with something called a Savitsky-Golay filter. So the best performance for them was that one, that LSTM with the Savitsky-Golay filter. It provided the best performance, where the goal of this filter was to remove any noise in the water data, just smooth things out. The last paper we'll talk about is from 2020 from two different water resources in Norway, from Oslo and Bergen. They didn't mention the size, but they mentioned that they collected the data from two different stations. They used 11 different water quality parameters where we can notice that they used almost all the indicators that we mentioned before. They tried to use an adaptive as their machine learning model. They used an adaptive learning rate network, backpropagation network, and a two-step isolation random forest model to predict individual water quality parameters as well. And we'll notice here two things. So the random forest gave us a smaller error, but the backpropagation network gave us a better stability with a larger data set. So all of these different papers, it just helps us conclude at the end that neural networks and deep neural networks and possibly like CNN and more complex hybrid neural networks would possibly be very beneficial for water quality prediction. So that's pretty much it. These are just the steps, like thinking how we could approach this problem. So first of all, we would deduce the optimal and possible types of different features that can be used or that can be retrieved from Egyptian water. Then we need to observe this water and analyze it. Then possibly find an optimal representation method, because I think I skipped over something. There isn't one water quality model. So if we look here and if we remember all the papers that we looked at, different locations, different countries use different water quality parameters. So we need to know which is available for Egypt and which is best to be able to characterize Egyptian water. So from that, we would get we would try to learn the best representation. Then we would enhance or propose and implement a computational model that would be able to target the different issues and the complexity of the water data to be able to predict water quality. And then possibly propose how this information, so when I predict the water quality index or when I predict the individual water quality parameters, how can I use it, or how can I send it to forecasting systems like decision support systems so that they can use it to be able to make decisions in the time of need. So yeah, that's pretty much it. Any questions? Yeah.
Thank you, Marwa. Yes, in order that the people that is attending online, I will give you the micro because if not, they cannot hear you. I will share the micro between Marwa and you. Yes, we begin to the people that are present in this room, and after that, I will give you the word the people that are on the streaming. Okay, what's wrong?
Okay, Marwah, thank you very much for your presentation. That was very nice. And okay, I have many questions, but here we had a project related to air quality, and that was remembering that issue and that problem. And okay, Cairo, I think it has both problems probably. Water quality, I didn't know, but air quality, I'm sure. Okay, so in air quality, we collaborated with people from environmental engineering, and they were using to predict. They were using physical models, physical simulation models. Are you aware of such kind of models to to model water quality also? I mean, they used for their quality, they predict their quality based on emissions and on potential emissions and on estimations on emissions, like from traffic, from industry, and also simulating the behavior of the air quality particles and molecules moving in the air with wind and with all that stuff. Are you aware of such kind of issues or of such kind of models that simulate the movement of the stuff in the water, simulating also the emissions to the river from the industries, from the sewage systems, from etc.
Unfortunately, I'm not familiar with that. But that's actually another very important point that I need to write down because I imagine it would be useful for the forecasting systems and the decision support systems to be able to like take this water quality information and then like give them the classification and tell them where it's predicted that this polluted water could move. So unfortunately, I do not have that information now, but I'll look into it.
Another one? Yes, David.
Hi. So thank you very much for the presentation because it's really nice. It's a really interesting problem. I don't have a question. I have a comment. Obviously, I didn't read the reference. I didn't read the bibliography, but according to me, there are two main problems. Seems that some of these references are focused on we have some input data and we want to predict another target data, another target value in this specific moment. And I think this because they are using some kind of models that you cannot use with time series. So it seems that there are some inputs and you want to predict an output, but in this specific moment, which is the value of this target now, according with this. And other reference seems that are working with a time series. So you have a big time series and you need to predict something in the future. And we have similar problems in the industry. In some specific problems, we can work with a specific with this time for predicting things in this time, and in other situations we need to predict in the future according with a time series. But the solutions are really different. And for you, this can be really important because, for instance, if you are working with time series, all the algorithms for future selections are different. Even the models that you need to use are really different. You need to work, for instance, with recurrent networks like LSTM or something like that. But if you are working in the other problem, in T0, some in the current moment, in the specific moment, probably it's easier. You don't need to work with these complex models. The future selection algorithms are always simpler, more simple than the others. So probably you need to have clear your objective because the algorithms the is a different situation, and for you will be probably more difficult to work with time series or with this or with time that without the time. It's a comment. It's not a question. And probably you want to work with both things. I don't know, but I'm sure that is really different, and I'm sure that the difficulty is also bigger when you are with the time for in the middle of the equation.
Yes.
Oh,
Yes, you're entirely correct. These are two different problems. They have kind of like similar goals, but not the same goal. I intend in my work, I intend on applying using time series data. But the problem is in Egypt, the work that has been provided, it does not use time series data. So that's why we looked at the at the first few works to just see what people do in Egypt. But it is my intention to use time series data. So you're correct. Yes, thank you.
Yeah, just one more comment related to this, and I think I agree completely with his comment. From the practical point of view, to predict what is going to happen in a specific point in the future is important. To classify, I mean, to get the index from what you have now, it is also important that we saw there, okay, what is the quality here based on pH, based on various variables, and you classify. it is also important the spatial one. And in the spatial one, you have to combine within special interpolation. And the same that happens in the time, that the best value to predict what is going to happen just next is what has happened just before. And close in time means close also in the value. The same happens in space. So in space also, there is this spatial correlation, and that happens also in time. So there are also models for that can be combined, and there are different problems. So prediction is fine, but temporal prediction is one, spatial prediction. So, and you have to focus in one of them. You have clearly identified that you are interested in the temporal prediction, but the other ones are also interesting problems. Yeah.
Thank you for your comments so much. They're very interesting. I will write them down because I need to think about what I need to do. So thank you.
Anyone more? No. Well, I have one question. In the past, we work in make an index for wildfire forecasting. Wildfires. Wildfires. Yes, wildfires. And analyzing the data that we must work with, we realize that the most important parameter is the weather forecast, because the temperature of the weather and the rain makes a big restriction with condition for to have a wild or not. I don't know if it's your problem, because the quality of water perhaps depends on the rain. If you are taking water from the river, because more rain, less percentage of contamination or not. I don't know. It's only a question.
Well, yes, you're also right. This will be clarified when we explore the data. So we need to explore and know, like, if we don't get much rain in Egypt, so like if maybe different locations are like are affected by different factors. So we need to still explore and find that out. But yes, that's right.
Thank you. Well, if someone that is following us by streaming have a question, I am open my speakers, or I can. Wait. Me siento como eco. Perhaps you can write down the questions in the chat and I can reproduce here. No? Well, thank you very much, Marwah, for your presentation. It's very interesting. Good luck for your research in the future. I'm sure that you will get it without problems. And thank you, all of you, for coming here. Perhaps we have during the lunch or later this week that she will be here until Friday. We can discuss or comment something more specific or something that appears during the week. Thank you. Thank you, Marwah.